Alright, so we talked about in the last video this bucket going around in a circle, and we said that the reason why the water doesn't fall out is because of inertia. Inertia is what keeps the water in the bucket, because at this point the water is going in this direction. And Newton's first law says that an object in motion will remain in motion, wants to remain in motion in a straight line unless acted upon by a force. Well, it is acted on by a force. Gravity is one of them, but it's not as strong as the force, the centripetal force being applied to it through the girl's arm and through the bucket. So what it's going to do is it's not going to stay on that straight path. It's going to stay in this curved path because of the centripetal force. Now, there is a point at which the water will fall, right? You know that. I can swing it slow enough for the water to actually fall out. And what happens then is what causes the water to fall out is the acceleration due to gravity, right? And that acceleration is, that's right, 9.8. I hope you said that, or I hope you thought that. 9.8 meters per second squared. Well, when that acceleration equals the centripetal acceleration that we're giving it, at that point, that's the lowest speed that we can go to keep the water in the bucket. When the centripetal acceleration, when AC is less than the acceleration due to gravity, that's when the water falls out of the bucket. I want to talk about this term centrifugal force. Centrifugal force versus centripetal force. I'm sure you've heard the word before, but the centrifugal force is that feeling of heaviness you feel when you are traveling at high speeds and you round a curve. If you turn left, your body wants to move to the outside of the curve, to the right. And that's called centrifugal force. This is the blank that you should fill in. Centrifugal force. It's a real phenomenon. It is something that's real. It's something you definitely feel. It definitely does exist, but it is not a real force. Okay? It's not a real force. So because it's not a real force, you will never put this on a free body diagram. So this diagram right here that shows centrifugal force pushing outward is not correct. The reason why it's not a real force is because it doesn't meet the requirements of a true force. Any force that we draw, we have to be able to pinpoint the source of that force. And if centrifugal force was a real force, it would be going toward the outside of the circle. So here would be a circle. If it was a real force, centrifugal force would point this way. Well, if there's a force that's going that way, there has to be something that causes it to go that way. Either something is pushing from the inside of the circle, or something is pulling from the outside of the circle. For instance, let's say you have a ball on a string. There's centrifugal force. Well, if the ball is on a string, the string does not push the ball toward the outside of the circle. If anything, the string is pulling the ball back toward the inside of the circle. That's what the tension of the string is all about. So the centrifugal force can't come from the string. And there's nothing on the outside of the circle that magically pulls the ball outward. So it is not a real force. It's something you definitely feel, but it's not a force, and it is a result of the inertia that we looked at in the previous slide. This inertia is what we tend to call centrifugal force. Again, it's a real thing, but it's not a real force. Do not put centrifugal force on any of your free body diagrams. I want to talk about vertical circles, but before I do that, I want you to just pick something. Let's see. I want you to draw something first. Let me insert a slide here so we can have a good drawing platform. Let's see. We're going to insert a slide right here, and it's going to be blank. Alright, we're just going to draw. We're going to look at a horizontal circle first. So here's a ball that's on a string, and it's being swung in a horizontal circle. Okay? And I want you to think about there's two forces that are acting on this ball at any one point in the circle. What are those two forces? I'll give you a second to think about it. What are those two forces? Well, one of those is very easy, actually. And one of those is a force that acts on us because we're on the earth all the time, and that's the force of gravity. And the force of gravity will always go down, pointing toward the earth. So with both of these, at any point, the force of gravity will always go down. Now don't forget that this Fg, this force of gravity, is the same thing as the weight. And I'll ask you this question once again: how do we find weight? Weight equals mass times gravity. Maybe I should change my color. How about that? Maybe yellow. There's another force that's going on, and this force is acted on through the string, and it is the tension force in the string, Ft. Got another force right here on this side. This is the tension force. Okay. Both tension forces point toward the center of the circle along the string where the string would be, and this is a horizontal circle. Now, in this case, the tension force is the most important force because it is the force that is holding this ball in its circular path. In a horizontal circle, the force of gravity, or the weight, has nothing to do with the centripetal force. It does not contribute to the centripetal force. In a horizontal circle, this is horizontal, there is only one force that's going to supply the centripetal force. And if it's a ball on a string, that centripetal force is the force of tension. So the tension force in this case is the centripetal force. Okay? Now let's talk about the vertical circle. As we said, weight is always directed downward. So let's make believe like this is our vertical circle. And I'm swinging a ball, I'm swinging my tennis ball on a string in a vertical circle. Okay? Still gravity and still tension force. Those are still the two forces that are acting at every point. And at every point in the same vein, my yellow arrows will be gravity. Gravity always pulls down. And now let's think about the tension force. Let's use green for a tension force. Think about the force of tension. What direction is tension going to be going? Let's say for this ball at the top, at position number 1. What direction does tension go? Well, at this point, tension will pull along the string, so tension is going to be downward. So this is tension. What about at the bottom? At the bottom, where does tension go? Which direction does our tension force go? Well, tension will again be going along the string. So tension will again point up in the direction of the center of the circle. And you can probably expect that tension on this side would go right, and on this side it would go left. So notice that the tension force is always pointing toward the center of the circle. All right. Centripetal force always points toward the center of the circle. And don't forget that the centripetal force is not one specific force. It's going to be the sum of all the forces that contribute to keeping that object in the circular path. In other words, it's going to be the sum of the forces that are going to be in the same plane as the centripetal force that's pointing toward the center of the circle. And the only place that's going to really matter is at the top and at the bottom. Okay, because at the top, centripetal force and gravitational force are going to work together since they're both pulling in the same direction. And if you can imagine swinging a ball on a string, at the top you can feel that the tension gets less than it does at the bottom. At the bottom, the tension has to be greater because you're actually fighting the gravitational force, which is less. It's fighting against your tension. The key is this. before, everything before, we've always done up was positive, down is negative. Well, now we're going to change it with circular motion, because now with circular motion, positive forces are going to go into the circle and negative forces are going to go out of the circle. And again, that only applies with the position at the top, and it applies with the position at the bottom. So at the bottom, the force of tension is positive because it goes into the circle, but the force of gravity is going to be negative. Sorry, that's not what I wanted to draw. Force of gravity is going to be negative because it's going out of the circle. But at the top, both forces, both the gravity and the tension, both forces are positive because they're pointing into the circle. And that's all we really need to say about this at this point. Later on, if we have time, we'll actually solve problems involving vertical forces. All right. So don't forget what I said before. In a horizontal circle, the weight or the force of gravity will never, ever act as the centripetal force. Centripetal force is what keeps an object moving in a circle. It's going toward the center of a circle. Gravity never does that, but it does play a role in the amount of friction a car on the road experiences. How does it do that? Well, the force of gravity is what pulls the car down, and the road is going to push back up on the car with what kind of force? If you remember from a couple weeks ago, the road pushes back with a force called the normal force. And it's the normal force that's determining the force of friction that keeps the car in the circular path, because the force of friction, if you remember, friction is fun. Friction equals mu times the normal force. Mu times the normal force. So this normal force, which is determined by the weight or the gravitational force, is going to determine friction. And friction is the centripetal force, but gravity itself will never actually directly act to add into the centripetal force, just in case you will need to know that later. All right, I think that's all we need to do for now.